All right. Well, thank you everyone for coming. My name is Tanner. I'm a developer at Nervos Network, and today I'm going to be going over writing smart contracts in Rust. So just a little background. Nervos Network uh, is kind of a collection of protocols, and the one of the biggest ones we have is called Common Knowledge Base, which is a layer one blockchain. We call it CKB for short, and it's a multi-asset store of value blockchain. We're going to be seeing a little bit about what the multi-asset part entails, and essentially um, we are able to create custom assets on top of the blockchain, similar to other smart contract platforms. And we're proof of work blockchain, and uh, it's more of a UTXO style blockchain as well. So generalized programmable UTXOs. Now, the reason we're able to write smart contracts in Rust is because our virtual machine is a bit different from many different virtual machines that you may see in other chains. And it's just a virtual machine based on the RISC-V instruction set architecture. So it's close to the hardware. And because of that, anything that compiles to RISC-V machine code is an available language for writing code and deploying it to the chain. So today I'm going to talk about the programming model, kind of the conceptuals in the background, and then go through somewhat of a simple smart contract design and development workflow. And then we'll get started on actually developing a particular system on Nervos. And throughout the course of this, you'll be introduced to a lot of concepts, and as well as a particular tool that we've released recently, which is kind of a framework for building smart contracts. And we won't get into everything like testing the smart contract, for example, because of time constraints, but I'll point you in the direction for learning more, and we'll provide a link to the repo containing the code that I write today, as well as the tests for that code as well. So first, let's go over the programming model. And I mentioned that our state model is a generalized UTXO. And the fundamental state unit is, we call it a cell. So on the left, you see that kind of from Bitcoin UTXOs, they have an amount and a lock, right? And we generalize this a little bit to 4 different fields: capacity, data, lock, and type. So capacity is measured in bytes, or what we call CK bytes, and that's actually the native currency of the chain as well. So a cell has a particular capacity, and it cannot occupy more bytes than the capacity indicated in its capacity field. Data is user-defined data, so that can be anything. It can be executable code, or it can be any sort of state that you wish to store in the cell, right? And then lock is similar to what you think about with UTXO lock scripts. So in order to spend or consume a cell, you need to be able to unlock it, right? And type is an interesting addition, which is another verification script. It's used to validate cell transformations. So whereas locks ensure that only the person or parties actually who can unlock the cell can spend it or consume it, and therefore they operate on inputs purely. A TypeScript executes on inputs and newly created outputs. Remember that because it's a UTXO style chain, the cells, a transaction which has cells as inputs and outputs, cells are consumed and destroyed when they're used as inputs, and created when they're used as outputs. So how do we get a sense of continuity of state? Well, we have these TypeScripts that operate on inputs and outputs to verify that the state change represented by the destruction of the previous state from inputs and the creation of new state outputs is valid according to some user-defined or developer-defined business logic. And it's actually these lock and type scripts which constitute the usage of smart contracts on Nervos CKB. And lock and type scripts, well, they're called scripts. They're actually this simple data structure, this map that has 3 fields. So there's the code hash, the arguments passed to the script, and then the hash type, okay? And basically, the code hash references a field on another cell. Either it could be the hash of the data or the hash of the type field of another cell. And the reason for this is that if you want to reuse a script, well, you have to store that script somewhere. So you store it in a cell's data field, right? And we'll call that cell a code cell. And then it's potentially the case that you want to use the code stored in that cell to verify many different cells. You want to attach it to many different cells. And so these lock and type fields are actually references to some other cell that contains the executable code. So the code hash references the cell by the hash of its data field or the hash of the type field. And that's determined by a combination of the code hash itself and then the hash type, which can be either data or type. If the hash type of the lock or type fields is data, then the code hash in that script structure is referencing the data field of some other cell. And for type, it's the hash of the type field. Right? So transactions then are 3 big fields: inputs, outputs, and dependencies. Now the function of dependencies is that, okay, you have these cells and inputs and outputs which reference other cells. And how do you find these cells? So it would be pretty difficult to scan the entire chain for those every time you run a transaction, right? And so actually what happens is that the dependencies or any sort of code cell that you need, or really even cells that contain data that your transaction might need, are included in the dependencies field. And the inputs, outputs, and dependencies from the script developer's perspective are all just cells, right? Cells with these 4 fields. In reality, though, just like in Bitcoin, the inputs are actually just out points. They have a transaction hash, which references the transaction that created the input as an output, and then the index of that reference cell in the outputs of the transaction with that transaction hash. And dependencies are similar. They're out points, but they have this additional field dep type. And the reason for this is that dep type can either be code or it can be a dep group. And a dep group, all that is a cell which actually itself references a bunch of different dependencies. And this is useful if, say, you have 3 or 4 scripts that you've developed, and maybe 2 or 3 of them are often used together. You can create a cell that's actually a reference, a collection of references to each of these other dependencies that you need. And then you can just use that. So instead of including explicitly many different cells in the dependencies, if those dependencies are always going to be included together, you just create a dependency group, and you only need 1 cell to load in multiple different dependencies, right? But that's kind of sophisticated. We won't really need that today, but it's just some background. And then, of course, these are the inputs and dependencies prior to script execution are resolved into the cells exactly like what you'd see in the outputs. So that's kind of a introduction to the state model and a bit of the program model. Now we'll go over a simple workflow for developing smart contracts. Essentially, yeah, the biggest part is defining the business logic, right? This is not just in smart contract design, this is in development in general. You need to understand the system and the rules prior to writing any code, right? And so once you define a logic, you kind of have two different things you need to understand. The initial state of your system once it's deployed to chain, and then the verification code that implements the business logic that that your system should follow. And notice here how since the chain is generalized UTXO style, smart contracts, or what we typically call them internally, are just scripts or verification scripts, are not these event-based scripts or contracts that live on chain, which you can call and then wait for them to perform some sort of side effect or update on chain state. Truly, they're just verification scripts. When they're included in a transaction, they ensure that the transaction satisfies some rule set according to whatever the code that the developer has written actually says, right? So, so you write the verification code, you write the initial state, and then, of course, the verification code cannot act on the initial state unless it's already living on chain. So once you have the initial state verification code, you deploy the code, and then you deploy the initial state with its references to the verification code that you've written. So the biggest part, like I said, is the business logic design, and this is kind of a simple modeling workflow that you can go through, which is before anything, you want to define the operations and queries that you want to support. Then you want to design the data structures, and that's essentially a process of determining what cells you need and what the cells data fields should look like, right? And then, since scripts or smart contracts themselves don't perform any sort of state updates, they merely verify transactions which describe a state transition, you need to translate your operations into transactions or transaction sets. So a transaction is analogous to an operation. So what we're going to be going through today is a simple decentralized exchange. And I remember I said that it's a multi-asset chain. And that means that users, developers, can create their own custom assets, their own custom tokens. And we have a standard, we have a few standards, but one of them is what we call the simple UDT standard, SUDT standard. That stands for just simple user-defined token. You can think of it as similar to Nervos Network's version of ERC20, right? So it's a fungible token, and we'll go over a couple of details about it. But basically, the purpose of this DEX is to allow users to purchase a newly created custom token with native capacity, right? So we can kind of think of it as an issuance lock. It's not really a DEX in the fullest sense of the word. It's just a lock script that allows users to purchase a custom token, right? And the operations we want the operations relevant to this is, of course, minting or creating the token in the first place, issuing, and exchanging, which is the act of purchasing the custom token by a user, and in return, the user pays the developer, the token creator, proportional to the amount of tokens they've purchased, right? So this conceptually depends on the UDT standard, or simple user-defined token standard. And so let's go over what a cell that complies with this standard looks like. And basically, on the right here, you see this cell, and its data field is an unsigned 128-bit integer. And the first series of bytes in the data field is then treated as the amount of that token, right? So if a cell is a token cell, then the data field is treated as the is storing the amount of that particular token in the cell. And then the type field here, of course, the code hash references the UDT code cell, which, remember, that's what I'm calling the a cell that contains the verification code, right? And then we have this thing called the governance block hash. And basically, the way that the user-defined token standard works is that if an input cell is locked with the governance lock hash, or with the lock script that hashes to this governance lock hash argument, then certain verification rules are basically circumvented or foregone. And what this allows is the developer to implement really sophisticated or simple, it's really up to the developer, governance logic while not needing to modify the verification code for the token itself. And this allows, for example, the person with governance permissions to mint new tokens after initial issuance, while, of course, preventing any user from minting new tokens. Otherwise, it would be kind of infinitely inflationary. And then the lock field of the token cell is up to the user who's holding the token. And this is interesting because if you contrast it to Ethereum, where these balances of particular custom tokens are stored in a contract that kind of acts like a registry, right? A mapping of users to their balances. This is not the case on Nervos. Rather, each holder of any custom token controls the cell that stores their tokens, and they have complete control over the ownership logic. This also introduces opportunities for high levels of interoperability between different on-chain systems. Because both type and lock scripts have access to the entire transaction, they can read any data within the transaction, and then block headers as well. But that's just an aside. That means that other systems, say for example decentralized exchanges or lending protocols, can interoperate with the token standard directly by simply providing a lock script that implements the custom logic for that particular system. And users can opt in simply by changing the lock field of their cell and participate in all these different systems with whatever custom token they're holding. So there's a lot of interoperability capabilities from this design. So in our particular case for the simple DEX, which is, like I said, really just an issuance lock, a way to purchase tokens, we're going to have the custom logic on the lock field. And that way, we can actually, when we issue a new token, we're simply placing a special lock on the token cells lock field, and users will be able to consume that particular token cell, and then create an output that transfers some of the tokens to themselves by essentially creating a new token cell with a portion of the amount held in the issuance cell. And then, of course, the issuance cell, which is the cell depicted here with the DEX lock, will have to have its data field modified for a decreased amount. But we can enforce things like the data field can be modified by users, but the type field cannot. Right? We can enforce these types of rules and allow people, any user, any potential purchaser, to consume this cell and therefore purchase tokens, so long as this same cell is created in the outputs according to certain rules that we'll define. So let's look at mapping these operations like minting and issuing to transactions. And you see here that I'm just depicting the transaction with inputs and outputs. And this looks exactly like how the token standard defines issuance, where the input is any arbitrary cell, but the lock field has to have the governance lock, and that's because the token script TypeScript ensures that the inputs and outputs store some total equal amount of the custom token. Now, of course, during issuance or minting, you're trying to create more output, you're trying to create more tokens in the output than in the input because you have 0 tokens in the input, right? So we need to indicate that this is permitted because we have governance permissions over this token. So we include that cell that's locked with the governance lock and the inputs. And the governance lock can be any lock script. And then the outputs, we create a cell that's the token cell. And we can see that this is the case because the code hash has basically of the TypeScript has the UDT definition, which is just another way of saying it references the cell that contains the code that defines the verification logic for the token. And what's interesting is that in our system, since we're creating this issuance lock, this DEX, the lock field of the token cell created in the outputs has the DEX lock as its code hash. And you notice there are 2 arguments here. One is the rate, and the reason we need a rate is that's going to indicate to us how much native currency, which is capacity, how much capacity does each token cost? And then the payee log, which is essentially a lock hash indicating the hash of the lock that a cell that's transferring native capacity should be locked with. So you can think of it as who is being paid for the tokens. Now, in our simple example, it'll probably be the same address that created the tokens themselves, but it doesn't have to be. They could have, the token creator could have an address reserved purely for receiving payments for this token. Right? And we see here that we have 3 different code hashes and on the different fields of the relevant cells. And that indicates to us that we need 3 different dependencies, right? We need the DEX lock, the governance lock, and the verification code for tokens themselves. Now, the governance lock can be anything, and in our simple example, we'll probably just use the default lock script that people have, which is just secp256k1 signature verification. And then we have the DEX lock, which is what we'll be coding, and the token, the UDT definition cell, that implements the verification code for the user-defined token standard is, we could write it ourselves, or we could use what's already deployed on chain, which is what we'll do. And the exchange operation is a little more sophisticated, where we actually have 2 inputs, right? So the first input is, you'll notice, the actual issuance cell, which is the cell containing the tokens locked with the DEX lock, right? The second input, of course, we need the user, in order to send capacity, in order to pay for the tokens they're acquiring, needs to consume a cell with enough, needs to consume a cell or more than one cell so that they can transfer enough capacity to the payee in order to verifiably purchase these tokens or validly purchase these tokens. And the outputs, we're going to enforce that a new issuance cell is created in the outputs. In order for this transaction to succeed, that issuance cell needs to exist on the outputs too, right? And the type and lock fields should remain exactly the same. The only thing that should decrease is the amount of tokens stored in the issuance cell's data field. We also have the second output, which is capacity, but locked by the payee's lock, right? And so that cell there constitutes a payment to the address the token creator has determined is the address that should receive payments in exchange for the custom token. And finally, the third output is a token cell, another one, a newly created token cell with its amount stored in the data field as the 128 bit unsigned integer. And you see that it has the type and lock fields. The type field is identical to the issuance cell because that that's responsible for storing the verification logic for this particular token. The lock field, however, is different. It's not the DEX lock. It's whatever lock the user wants to attach to it because the user owns it, right? And we'll have to enforce rules about the fact that the data in the output issuance cell is equal to the data in the input issuance cell minus the amount of tokens purchased, for example. These are all rules that we'll have to think about. So just to recap, what this state change is doing is we are decreasing the amount in the issuance cell between the input and output. So the purchaser is making this change. Then capacity, which is once again the native currency, is sent to the recipient who should be receiving payments for purchasing tokens. And then the custom token, some of the custom tokens proportional to how much capacity we've paid for is then sent to us, basically. Or if we're the user, if we're the purchaser, then we create this output and send some custom tokens to ourselves as well. So that constitutes what the operations will look like for both issuing and exchanging. And because of that, we understand what our initial state is going to be. It's going to be that particular issuance cell which is just a token cell with the DEX lock, right? And in order to go from this to an actual on-chain system, well, first we need to either ensure that these dependency scripts already exist on-chain, or write them ourselves and then deploy them to chain. And after that, we'll deploy the initial state. So now we'll get into some of the actual smart contract development practices. And what we'll be doing is using a new tool that Nervos released called Capsule. Capsule is a framework for developing scripts in Rust. So you are provided with boilerplate, you can create projects, and you can then develop scripts. You can write tests for those scripts, and you can also deploy those scripts to a local developer chain, testnet, or mainnet, all from Capsule. And Capsule creates a couple different modules for you. And we'll see this itself, but you'll have the build for the contracts that you actually compile, the contracts module where you actually develop your contracts, and then the tests. Okay, so I'm just going to pull up capsule now. And before we go into developing, I want to show you some useful resources and links that you can use. So capsule is Nervos GitHub, on GitHub, Nervos Network/capsule. It has a great wiki here that walks through setting it up and actually building or implementing the user-defined token contract. So it's a contract that's compliant with the user-defined token standard. And what's actually interesting here is that Capsule uses these other libraries. And the Rust using Capsule is actually no standard Rust. So kind of think of it like embedded systems development. However, we provide CKB, something a library called CKB standard and CKB types, which allow for the use of richer data structures and system calls for this no standard Rust, right? And the documentation for these is very useful. I'll probably have to refer to it myself during this little demo here, but we see that CKB standard has these various modules, and the three will be using the most is CKB constants, high level, and syscalls. Now syscalls provide support for all the system calls that a script can execute, right? So if we want to load a cell or we want to load a script, load a transaction, that type of thing. And then high level are kind of these nice wrappers around the system calls to provide an easier interface and some additional functionality, right? So technically, all of the things included in high level, all of the functions, you can achieve all of this functionality without using the high level module, using purely the system calls and syscalls, but it's easier to use this when needed. So then we have that, and then we also have CKB types, and the bulk of it is in the packed module, which provides these data structures out of the box for all of these different types of data that the system calls and whatnot might return. So if we just go to outpoint, for example, we can load in an outpoint, and that at the system call level, that may be just a series of bytes, but we can initialize an outpoint structure from those bytes, and all of a sudden we have access to these simple methods that can allow us to extract the transaction hash in the index, for example. Okay. So I'm just going to pull up the code editor. We'll get started on actually coding some things up, and really, due to constraints here, we'll just be kind of sketching out a skeleton of the project, get to some of the functionality, but I'll provide a link afterward so that you can get into more depth on developing the script and writing tests and seeing the full code that results from it. Okay. Okay, so I have my code editor up here, and I have Capsule installed already. Capsule is really easy to install, and you can follow the GitHub repo wiki, Nervos Network/capsule for that. But I'm just going to create a new project, Unitized Workshop. It already exists, so I will create one called Simple Dex. And that's just a capsule new command, and it's going to create all of these things for us. So it's creating a couple of packages. The the actual binary package and the test as well. So we'll go to that now. And see. Frankly, I don't usually use this text editor, so I forget how to open or enable the command line options. So I will just go this way. Okay. So we have this, we have our structure. Skip that for now. We have our structure here, our project structure. So there's build, that's where the contracts we actually compile are. And where we're going to be working is really inside the contracts in the main RS. So like I said, it's no standard. So there's a bunch of setup here for using core instead of standard library. And then we have these are imports for our actual, for our CKB specific libraries, and we can change these as well. And this is just the template that Capsule sets up for you. And then this we can ignore, right? This really just ensures that the system API of the virtual machine is followed, and really it's going to call this main function, which is defined below. We also have this error enum here where we can define our custom errors, and it'll just work, right? So this is the main function. You can see it's remove below examples and write your code here. So this is where we get into where we'll write our code and execute it. So I'm going to get a terminal and running to make this a little bit bigger. Okay. So what's one thing that we want to basically ensure? Remember, we have 3 outputs in our expected exchange, right? So the first output is the issuance cell. The second output here is the payment cell. The third output is, of course, the user's custom token cell that they purchased, right? So, of course, we need to enforce a certain set of rules on these things, right? And before we do any of that, we really need to be able to load in the issuance cells and ensure the rate, right? And so that's what we'll do, is we will focus on loading in the issuance cells, or certain parts of them at least, right? And so let's do, and we also want to load in the arguments, right? Because the arguments contain the payee lock and the rate. So that's what we'll do. So we see that there's already this system call for loading the scripts, and we unpack it into bytes. And bytes, we can bytes just data structure, but we can compare them with vectors of bytes or arrays of bytes, etc. So there are 2 arguments here. 2 arguments. The first is the rate, which denotes capacity, right? And capacity, or CK bytes, is a unsigned 64-bit integer. And the second argument is the payee lock. And the payee lock is going to be a 32-byte hash of a lock field, right? So because of that, I'm going to define two things here. Rate bytes, which is just going to be a byte array. It's a 64-bit number, so it's going to be 8 bytes long. And then I'm going to do the same thing for the payee lock. And this is basically, I'm just trying to get these into their own data structures outside of the args bytes, which is just easier. Not necessarily the best way always, but easy to reason about as we kind of develop a prototype here. And we can, of course, from these arrays, we can copy from slice, which is a method. So we can copy the contents of a slice from somewhere else to these arrays. So that's what I'm going to do. And we want the first 8 bytes from the args. And then for payee lock bytes, we want basically the rest of them, right? Now, right now, this contract is assuming that those are the only 2 arguments, and that's the assumption we're going to make for this particular prototype. And then it's in the byte order for the CKB virtual machine is in little endian. So we're actually going to make the rate itself. Remember, it's a U64 from the bytes of the rate bytes. So we can just pass rate bytes in. We won't need it again. Right? It's only necessary to get this rate. So now we have the rate and the payee lock. That's just an array of bytes. We don't really need to do anything else to it after that. Now we need to, let's see, what do we want to check first? Let's check that we're loading the issuance cells, because we want to load in the issuance cells, and then from the difference in the issuance cells amount field, that will allow us to get the actual amount that the user has to pay. So we will say issuance cells equal load issuance cells. And notice that this returns a result. This main method returns a result. So we're just going to make the error handling simple. And so once we have load issuance cells, which is just a hypothetical function, we don't have it yet. Once we have those issuance cells, we need to calculate the minimum payment. And the minimum payment will need 2 things. It'll need the issuance cells so that it can check the difference in the amount fields. And it will also need the rate, so it can use the rate and the amount amount that the user has purchased in order to determine the final fee or payment that the user must provide. So we'll calculate min payment. Just the second function we don't yet have, and that's going to take the rate. And U64, it's a copy type. So if we pass it in, we don't have to worry about any sort of ownership issues necessarily. I'm pretty sure. I actually have to check the documentation to ensure, but yeah, it's a primitive type, so it should be copy. And then we would need the issuance cells, right, which are going to be custom, probably for making it easier. We'll have this load issuance cells be probably a tuple of 2 custom structures for us, right? And that's also going to return error handling. And then once we know the minimum payment, we probably want to get the payment amount. Now, in order to get the payment amount that the user actually paid, we will probably need to check which outputs are locked with the particular pay lock, right, with this lock, and check that the capacity, the sum total capacity of those cells is equal to this, is at least equal to this minimum payment, if not greater. You're always allowed to pay more, right, but you can't pay less than the minimum. So we'll say that let payment amount and that will take the reference to the pay lock bytes. Payment. And then the big logic that we want is basically if the minimum payment is greater than the payment amount, we need to return an error, right? So we return an error, and we're going to use our custom errors here. Payment not enough. Now, this error doesn't exist yet, but what we can do is we can scroll up and just add it here. Now that error is valid. It's valid error code. Okay, so let's focus on loading the issuance cells, and that's probably all we'll have time to get to. But like I said, I'll provide the GitHub link to see all of this code. So what does load issuance cells take for an argument? Nothing. Okay. And load issuance cells, it's going to return a result. We know that. And it's going to return, like I said, a tuple of issuance cells, right? One for input, one for output. So I'm probably going to define this custom type here. And then return an error. And so I actually have to define the structure for the custom structure of my issuance cell, right? And the issuance cell, let's define it here, has a couple different things. So we want to indicate if it's from the inputs or outputs. So it's going to have this source. And the CKV constants defines this enum of source, which can indicate an input or output. We of course have to include that here, right? So that's CKV constants. So we're going to include those, and that allows us, that'll bring in this source enum for us. Now the data is going to be a vector of bytes, right? So we're just going to say vector of bytes. It's going to have a lock hash too, right? And we need that because we want to ensure that the lock hash doesn't change. The data is going to contain the amounts, which we'll want in order to compare and determine the minimum payment amount. And the lock hash, well, we need to ensure that the issuance cells, the lock hashes remain the same. So, and that's going to be, we can just make that statically sized array because the hash is going to be 32 bytes long. The index, so we might need to access these issuance cells later or access other fields in them through other syscalls. So it's nice to have the index of the cell in the inputs or outputs. It's going to be usize. And then finally, its capacity, right? We're going to want to make sure that the capacity doesn't change. Even though a purchaser is purchasing this issuance cell, I want to make sure the capacity hasn't changed. Okay, so in order to load the issuance cell, how do we know if a cell is an issuance cell? Well, essentially, it's going to have a special lock hash, right? And a script has access to everything in a transaction, including itself. So we can use this cool method, it's this call called load script hash, which will return the script hash. And that's a high-level method. So we need to bring it into scope there. And I'm just going to refer to the documentation and check if that returns an array, or probably an array of bytes. Yep, it returns a static sized array, 32 bytes long. Okay. All right. So I have that, and I can actually look for the input issuance by iterating through the outputs, right? So what I'm going to do is keep track of an index here. I'm going to loop, and I'm going to check that actually I can use a special structure that's inside of the high level called query iter, which allows us to kind of query the transaction and search for certain things with a custom iterator. So I'm going to say that this is just input issuance cell. That's what we're looking for here. Equals, and then it's going to execute a particular system call, such as loading the log hash on all cells from a specific source, and we're going to say source input. So I have to bring in load cell log hash, which also happens to exist in the high level there. And so I will back down here. All right, and this provides a way to, it's just an iterator, so I can execute. I have a bunch of different functions I can call that take closures. So I'm going to use find here. It's going to pass in the result of this system call to the closure. So find log hash, and basically I just want to check that the log hash equals this log. So if their bytes are equivalent, then I want to return that result. And I want to actually keep track of the index, because remember, I want to return from here issuance cells, and so I have to keep track of that as well. Okay, so once I'm done with that, I just want to check if I want to handle the case where it was not found, right? And if it wasn't found, basically, this whole iteration is going to return either it's going to return an option with a wrapped value. So basically, if we can check if it's some or none with this method here, and then if it isn't some, that means that it did not find it. We want to return an error, say cannot find issuance, something like that, right? And then just like before with our workflow, when we define a new error, we want to define it in our custom error enum. Okay. So, and then we'll basically do the same thing. Well, we will do the same thing for output. Let's just load in some other portions of the issuance cell. So high level module also has a load cell capacity. And since we have this I here, now I'm pretty sure that this will stop at the first instance that it returns true, right? So I'm pretty sure that after this iteration, I will be equal to the index of the issue itself. But like many people, I don't remember all of these things off the top of my head, so I have to check the documentation. But for now, we'll just assume, right? And tests, writing tests later helps flesh out which assumptions were correct and which were not anyway. So I can load cell capacity by passing in the right index and then the source. So I'll say source input. And all system calls return, have that result return. So we're just going to handle them with the convenient syntax here. So I have the incapacity, and I also want to load in the data. So we'll say in data equals load cell data. And then I will initialize my structure. So this will be one of the issuance cells that I return. And I give it the index, the source we know is source input. And what else does it need? The lock hash, the data, and the capacity. Okay. So we need capacity. You can just take ownership of these things. And finally, the lock hash. Now, the lock hash will just basically clone that for now, so that it has its own copy there. And that's going to be the issuance cell. Now, we'll just do the same thing. We do the same exact thing for outputs. Then we return basically a result with issuance cell, say, input. And we do the same exact thing, return another one, issuance cell output. But due to time constraints, like I said, we're not going to be able to get through nearly all of this functionality. But some things to take away from this are that there's a pretty straightforward workflow here. Especially one that I like to follow is I just define the high-level logic with these hypothetical functions, and then I begin implementing them one by one. And as I need new errors, I just scroll up to this nice error enum that Capsule provides, and I write in my errors. And as I need new system calls, like load cell log hash, load cell capacity, and load cell data, I'll just add those in, right? And in order to do this effectively, it's very useful to have the documentation open. And like I mentioned before, the documentation, the best way to find it is by going to the Capsule wiki on GitHub, going through the tutorial first, of course, and then looking at the various libraries it depends on, like CKB standard and CKB standalone types, and then switching back and forth between coding and reading those whenever you need to, because you know, a lot of stuff returns a lot of calls return byte arrays, and you can use the types in order to cast those collections of bytes to particular data types, and make things a lot easier, right? So that's really all I have. If you're interested in continuing this exploration, since we've only just begun coding up this script, I welcome you to go to the GitHub link, which I'm about to show you. If I can pull up the slides again here, and look at the complete version of this code, as well as the tests, because it's probably the case that some of the things I wrote in this demo may fail tests, right? So that's why we have tests. Anyway, here is the link, Wilfred TA/Unitized workshop for the completed version of the code. And that's all I have. Thank you for joining, and happy to take any other questions that people haven't asked yet. And feel free to submit issues or something there if you see anything wrong, or you want to add any functionality yourself. All right, thank you.